hesitation, infrastructure planning for unmanned vehicle navigation in constrained environments. I'd like to thank my committee members for giving me the opportunity to work on such interesting topics, for providing valuable feedbacks and helping me out during the course of my research. So throughout this presentation, I'm going to talk about localization and optimization techniques that help in vehicle navigation in GPS-denied environments. The common factor binding the different topics is the degree of information available to the vehicle prior to the navigation step. In particular, whether the sequence of the waypoints are available, whether the system requires global features or landmarks for localization. If yes, whether the routes and these features are optimally selected or placed or not. Each problem is divided based on these factors. We have validated the efficiency of our algorithm through extensive simulation and hardware testing. Hardware development played a major role during the course of my research. Therefore, I'm going to be talking about it briefly in the end. Finally, time permitting, as part of the future work, I'd like to talk about a few approaches that are explored during my research but not particularly used. Nevertheless, these are very powerful techniques that can be used to solve challenging problems. The three key factors that should be considered for navigation are mapping, localization, and path planning. Optimal strategies to build the map of the environment and efficiently route a vehicle or a group of vehicles are essential for effective navigation. So, for a vehicle to localize itself within a region of interest, it needs to have sensors. These sensors can be internal, such as IMUs or internal measurement units, wheel encoders or odometry, or external, such as global positioning system or GPS, range tags or vision tags. However, just having good sensors is not good enough. For the sensors to work properly, they need to pick up meaningful and appropriate information from features in the environment. These detection and data gathering steps require computation and data association. The most common external sensor that path planning and routing algorithms use is Global Positioning System or GPS. However, GPS has a plus minus 5 meters of uncertainty in north and east direction and plus minus 9 meters of uncertainty in height. So if GPS is unavailable or unreliable, we need to resort to alternate data gathering methods. If the features in the environment are known, we can perform a known feature-based localization. If the locations of these features are unknown prior to the navigation step, we need to perform simultaneous localization or mapping, at least estimate the position of the features along with the states of the vehicle. So each of these steps involves some degree of computation, and definitely the measurements require data association. So optimization is necessary. Optimizing sequence of waypoints, that is routes to travel through, improve the routing efficiency. Optimal selection or placement of features, also referred over here to as landmarks, to perform successful localization with minimum features decreases the infrastructure development cost. It also reduces the data association cost. It increases the computational efficiency by reducing the storage and computation requirements. Jointly, these can be categorized into mapping and path planning optimization problems. So the questions that immediately follow are, what if meaningful features are unavailable? What if the exact locations of these features are unknown? What if GPS signal is unreliable or unavailable? What if the environment poses other constraints, such as having repetitive structures or walls within which the vehicle is required to navigate, as shown in the figure? These kind of environments can be collectively termed as feature deficient and constrained environment, also GPS denied. In such scenario, we can try to do optimal feature injection for precise map building, as we did for our final work, node-to-node estimation and localization for approximate map building, and augment techniques like short interval path planning and active collision avoidance to improve navigation. During my research, we solved localization and optimization problems with focus on optimizing resource utilization. We developed conditions following which our algorithms are guaranteed to work. Incrementally, we have explored problems and with added constraints and challenges. In order to solve optimization problems, we explored and developed classical techniques such as mixed integer linear programming, evolutionary algorithms such as deep neural network for function approximation, and gradient-free techniques such as particle swarm optimization and colony optimization, etc. For my final problem, we have leveraged the advantages of both the worlds to develop a hybrid optimization strategy for feature injection in an otherwise feature deficient environment to enable localization. Keeping the presentation duration in my mind, I'd like to present an overview for the first three problems and discuss the last problem in details. Moving on to the first problem, that is vehicle path planning with localization constraint, or VPLC, or as we like to call it, traveling salesman problem on steroids. In this problem, our goal is to solve a combinatorial optimization problem using mixed integer linear programming architecture to jointly reduce the traveling cost and landmark placement or selection cost by improving resource utilization. We are given the starting location of the vehicle, a set of waypoints to travel through, but not the sequence of waypoints. And we are also provided with potential landmark placement locations from which we need to select a subset of landmarks that can ensure proper localization. We are required to travel through the set of waypoints exactly once, adhering to the localization constraint. That is, the vehicle is required to maintain path to at least 2 known landmarks at all the time during the course of the travel. The benefits of optimization are better resource utilization, especially perishable or limited resources such as fuel or battery, improve computational efficiency, and most importantly, reduce the overall infrastructure planning and development cost. Now, for this problem, we optimize the route and associated landmark locations prior to the navigation step. For optimization, the two most important papers for reference are S. Rathinam and al. Solved greedy optimization algorithms, assuming the route is already solved or known. They ensure that the landmarks are placed optimally such that the localization constraint is satisfied. K. Sundar and al. Improved upon this work by developing faster heuristics. For localization, Y. Song and al. and R. Sharma and al. Prove that we need path to 2 known landmarks at all the time for a system to remain observable. Observability is a measure of how well the internal states of a system can be inferred from the knowledge of the system's external output, that is, its current states and control efforts. The major contributions for this work are: we solve a joint optimization problem using range-only or bearing-only sensors. We considered practical sensor limitations such as sensing range or field of view. We adhered to the localization constraint. We developed a very efficient subtool elimination technique enabling efficient optimization. And finally, we validated our work through extensive simulation and hardware testing. Figure 6 represents the system architecture. The map is developed offline as the optimization is done prior to the navigation step. It provides a sequence of waypoints to travel through and the location of the subset of the landmarks that are selected and placed, using which the vehicle can successfully localize and navigate. This slide shows a set of linear equations and constraints that we're using to solve the optimization problem. In particular, using these equations in a mixed integer linear programming architecture, we are jointly reducing the traveling and the landmark placement cost. In this representation, as we can see in figure 7, is for a directed graph. Equation 1 and 2 ensures that each waypoint has 2 associated edges. Equation 3 is the subtool elimination constraint. Equation 4 is the localization constraint. XE is a binary constraint determining whether an edge or path between 2 waypoints is selected or not. YK is a binary constraint that determines whether a landmark is placed at the kth location or not. CE and DK are associated costs for travel and landmark placement, respectively. So we are using a directed graph as we are considering the field of view criteria for the sensors. Now, figure 8 shows a very interesting result for the subtool elimination constraint. For subtrue elimination, we use a robust dynamic cut generation technique. That is, the SEC or subtrue elimination constraint is initially relaxed. We find a feasible solution to the relaxed problem. If a feasible solution is found, then we check whether that feasible solution is also a valid solution for the actual problem. If it is not, then we introspect the subset of waypoints, waypoint sequencing that violates the SEC. We add back the SEC and obtain a route with the subtrue elimination constraint for those subset of waypoints that is violating the constraint. This way, we reduce the number of subtrue elimination constraints from being 2 to the power 2 to the power t, where t is the number of waypoints or targets, to a handful of 10 to 20 constraints for 15 to 30 waypoints. This exponential term is pretty huge, even for 15 set of waypoints. But the dynamic cut generation greatly enhances the speed with which the optimization algorithm can find a good solution. This set of figures highlight the result for the optimal route and associated landmark points. Results highlighting the importance of joint optimization instead of having potentially non-optimal solutions are discussed in the thesis as well as in the respective papers. We are given 15 waypoints to travel through an associated landmark placement point. In figure 10, we see that using the joint optimization, we find the optimal waypoint sequence and associated 8 landmark locations that can keep the system observable. This is highlighted in figure 11. We see that the system is not only observable, but the uncertainty bounds or the 3 sigma bounds for the position and orientation of the vehicle remains tight as well. These results correspond to the hardware runs we performed using open loop trajectory and bearing only sensors using barcodes. We have a dedicated section for the hardware development. So figure 12 and 13 corresponds to a run that we did using estimated states, and figure 14 and 15 are the results corresponding to the same trajectory we obtained using true states via the motion capture system. We see that using 4 optimally placed landmarks, the vehicle can successfully localize and navigate. That is, the system has tight uncertainty bounds. It is observable as the bounds are decreasing with time. We also performed a closed trajectory run with AR tags providing range-only measurements. So at any given point in time or trajectory, the vehicle has path to 2 landmarks. Using these optimally placed landmarks, the vehicle was able to route through the given set and sequence of waypoints. This is shown in figure 16 and 17. The route is obtained using estimated states. It can be seen in figure 17 that the system remains observable and the bounds are tight and decreasing with time, even for this system. These were the related papers. Yes.
I'm not able to see those figures. Were you showing the figures? Okay.
These are the figures 16 and 17.
Okay.
Yeah. Okay. All right. So these are the related papers that were published pertaining to the VPLC problem. In this work, we addressed point 1 in a global frame. That is, the optimal route and the global landmark points are known to us before the navigation step. In the next section, we discuss a solution to a problem that is developed in a relative frame of reference. We talk about cooperative timing arrival or simultaneous arrival problem now. In this problem, our objective is for n agents distributed geographically to be able to converge onto a moving and maneuvering target in a GPS-denied environment at the same time using cooperative relative localization technique. We know the initial location of the agents and how far they are from the targets. The agents have limited sensing range and field of view. At least one agent has the targets in its line of sight, and this was proved using the observability analysis. Although global landmarks may help, we did not require global features to solve this problem. The main points for this slide are R. Sharma and S. Rathinam solved a very similar problem for static targets. However, moving and maneuvering targets adds its own set of challenges. To develop a proof of concept for this solution, we considered a cooperating target. That is, we know the velocity and turn rate of the target by accessing the target's IMU. But in case the target is non-cooperating, the velocity and the turn rate for the target can be easily estimated using relative position estimation concept developed in 9 and 10. To highlight the major contributions, we solved a simultaneous convergence problem in a GPS-denied environment using PN guidance and relative cooperative localization techniques under the assumptions A, the forward velocity of the target is greater than that of the forward velocity of the agent is greater than that of the target. The maneuvering capability of the agents is greater than that of the targets. And the agents can share range information with their neighbors as long as they're in the sensing range. This problem is formulated in a target-centric formulation. This obviates the need of additional frame transformations. Finally, we performed observability analysis to come up with conditions under which our algorithms will work. The estimation model shown here is developed in a polar coordinate system, where rho is the distance between the agent and the target, theta is the line of sight or LOS angle, psi is the heading angle. We can see that the rate of change of heading, a psi dot, is influenced by the lateral acceleration component A. And we can also see that we are assuming a constant forward velocity, so V dot is equal to 0. By the definition of PN guidance algorithm, the rate of change of line of sight or theta dot is equal to 0 and will remain 0 only when the agent reaches the target location. The target model is assumed to be a simple 2D model. Now, if I may point your attention to figure 20, we see that A1 is closer to the target than A2. Assuming the target to be static for ease of explanation, if the agents have the same forward velocity, A1 will reach the target faster by traveling on a straight line joining A1 and T than A2. Note that we do not require the velocity of these agents to be the same. Nonetheless, their forward velocities are assumed to be constant. So if we can change the lateral acceleration of A1 and force it to take a curved path, we can match their arrival time or time to go. The equations express the exact same thing. We can tweak the individual lateral acceleration terms by measuring the difference between the time of arrival for each agent and its neighbors. This is used to modify the variable navigation gain or n bar. And in turn, we can use that to control the lateral acceleration, which is equal to n bar v theta dot, where theta dot is the rate of change of LOS, v is the forward velocity, and n bar is the variable proportional gain. Coming to the observability analysis, we divide the system into two subsystems, one for the bearing measurement between the agent and the target, and the other for the intervehicular range measurement. With the intervehicular range measurement and connected graph, we get a rank 2 efficient system. With the bearing measurement, the subsystem is full ranked as we only concern ourselves with rho and theta, which is in the polar coordinate system. Therefore, using the combination of the two, we get a full ranked total system. The figure shows a collision triangle. Practically, we may not require to switch between different guidance laws. The exterior of the collision triangle is a region where theta dot is not equal to 0. This is going to be true for PN guidance based navigation till the concerned agents reaches the target. The interior of the collision triangle is a region where theta dot is equal to 0. If this case arises, two agents would need to have the targets in its LOS or line of sight for the system to be observable. But this is a practical assumption, as agents will already be very near to that of the target and almost be like in a tail chase mode. The intervehicular range measurements is unaffected by the collision triangle. We also developed other practical constraints, such as avoiding perpendicular travel for a long duration, or not having a huge difference in the initial ranges of the agents that are required to maintain an effective solution. We see that using algorithm, 4 agents can reach the moving target at the same time using the estimated states without needing any external global features. So we can see that a difference between the slowest and the fastest agent is less than a second. It was about 0.6 seconds for a 1000 cross 1000 meter square area. We also see that further, if we have a target that moves at 80% at the speed of the agents, they are still able to successfully converge onto the target at the same time. We also validated the same on hardware using fixed convergence point. Unfortunately, I don't have a better hardware video, but this work, along with a target handoff problem, was validated on hardware using ground and aerial vehicles at AFRL. We solved a scenario where we did not have a fixed prior route or access to global landmarks. Nevertheless, this localization setting is developed in a relative framework. In the next sections, we solve problems in global settings with limited feature availability or unknown prior routes. Next, we talk about the area coverage problem for search area optimization. During the course of this project, our main aim was to explore, understand, and use evolutionary algorithms to solve optimization problems. We were able to develop a sense of cost function, constraint construction for evolutionary methods or gradient-free methods while working on this project. Even though this problem could have been addressed with techniques such as classical techniques such as MILP, we explored PSO, ACO, neural network, that is particle sum optimization and colony optimization and neural networks, etc. over the duration of this project. So for this work, we are given a known region containing obstacles. Our objective is to distribute waypoints in this region to maximize the area coverage. Assign a subset of this waypoint to individual UVs in a group of multiple UVs and allow them to route through the environment efficiently while avoiding obstacles. The waypoint distribution is achieved through a novel particle swarm optimization, especially the initialization of the PSO. The routing problem is addressed using ant colony optimization. The obstacle avoidance is achieved using artificial potential field, or APF. Even though APF could be extended to address active collision avoidance, we saw that it severely slowed down the simulation, and hence the collision avoidance was left out during the implementation, as it was causing implementation issues. These are some of the literatures on evolutionary algorithms, their advantages and disadvantages, how to formulate the cost function in such settings that we explored during the course of this work. The major contributions for our work are, we formulated a PSO with a novel initialization method and supported cost function that will guarantee to provide solutions in the feasible region only. Traditional PSO formulation may include infeasible solution in their initial pool if careful inspection is not taken into consideration. We modified the structure of PSO to support parallel processing. We developed two methods for the partitioning problem based on the user need. That is, whether they would want a strict search for intruder detection or rigorous surveillance, or a segmented or fuel efficient search to address problems like animal herding, observation, or search and rescue operations. The solution architecture enabled cooperative localization, as the agents can share information among each other. The environment contained local features to support GPS-denied navigation. We also have a provision to switch between one method of assignment to the other method on the go if it is at all required. Moreover, the strict search method also had an added mechanism to dynamically assign routes to the individual UAVs while they are navigating. This provides an increased degree of unpredictability so that the potential intruder cannot perform stop and go maneuver to beat the system. The system architecture for this system is similar to the VPLC problem. However, the offline step addresses a different set of optimization criteria in comparison to the VPLC problem. Moreover, we are using a cooperative localization for multiple UAVs instead of routing a single UAV as we did in a VPLC problem. Now, the two main optimization problems that we are addressing are area coverage or waypoint distribution and traveling salesman problem, or TSP. We approximate the region to be a convex polygon, as concave shapes lead to locally optimal regions. Imagine a UAV flying at a constant height with a downward facing camera. So at any given point of time, it will be able to cover across a circular cross section or area of pi r square, where r is the radius. This forms the basis of our waypoint distribution. So initially, we cover this convex polygon with a rectangle deploy or assign waypoints using grids and eliminate any waypoints that is lying outside these grids or inside the obstacle. And then for every particles, we assign a little bit of uncertainty or noise for the particles with this waypoint so that they are distributed uniformly, but also with some amount of difference in the space. This forms the this guarantees that the particles will contain feasible particles in the swarm. So the cost function associated with the environment dictates the feasibility criteria. The two other cost functions are normalized between 0 and 1. CF coverage is used to maximize the area coverage, and CF overlap is used to minimize the overlap between the waypoints or the individual search regions. Together, these three makes the total cost. This structure ensures that no infeasible solution are initially produced. It efficiently rejects any infeasible solution outright, even if they are generated, by pushing the cost of this infeasible solution. As you can see, the NOC criteria in the CF environment, this particular factor pushes any cost of the infeasible solution to a value greater than any feasible solution, the maximum cost for any feasible solution. This way, the infeasible solutions are immediately rejected. Using the waypoint distribution, cooperative localization, APF, the UAVs can route through the sequence of the waypoints assigned to them. The PSO generates a monotonically decreasing cost, as can be seen from figure 32. And we are, as figure 31 shows, we are using ACO to handle the traveling salesman problem. So we ran the simulation for two cases, the strict and segmented case for 10,000 seconds. MTBR represents the mean time before revisiting the waypoints. For the strict case, we also assign priority waypoints, priority to the waypoints that are required to be visited by more than one UAV before they complete their individual tours or loops. The essence of the area coverage algorithm is captured comprehensively through this visualization. The top row corresponds to the segment, the segmented search scenario. We see that UAVs route through the local subsections of the map in the segmented search. Even though this improves the fuel efficiency, that comes at the cost of allowing minimum overlap with individual segments. So this is not a very great technique for strict surveillance. The bottom row plot corresponds to the strict surveillance case. We assign 8 priority waypoints on the edges that are required to be visited by 2 UVs per their individual tours. This can be clearly seen from the higher heat concentration in those regions, as well as through the MTBR plot. The MTBR values for those waypoints are almost at half of the other waypoints. Since the user have the option to switch from one technique to the other, this can be done to create a more uniform heat map. As the two maps in this region shown over here has very different distributions, they can be combined to develop a uniform heat map. However, in the future, this heat map can be actively used to temporarily assign waypoints in cooler regions such that an UAV or a group of UAVs can frequent those points or spots to generate a more uniformly distributed heat map without needing to switch between the two techniques. These are the related papers that were published for the two previous works, that is the cooperative timing arrival and the search area optimization. And this technique addresses point number 2 on a global frame of reference. In the next section, we talk about a hybrid optimization strategy that combines the advantages of MILP and machine learning to enable vehicle localization by optimally deploying features in an otherwise feature deficient environment. This is pretty interesting as we haven't come across any previous work that handles feature deficient navigation using this kind of a solution architecture, keeping future missions in their mind. In this work, we consider an environment like a tunnel or a mine that can be considered to be dark, containing repetitive structures. The vehicle may be confined to travel within a tight space that is confined within walls. And since it's a closed environment, it may receive poor or no GPS signal. We are given the starting location of the vehicle, a couple of known landmarks near the depot or the starting location, and at least the maximum distance that the vehicle is required to travel. Our goal is to localize and navigate in such environment. We address this by injecting range-based beacons in the environment to act as information source. So relying on this, the UV can localize itself. Since the vehicle can carry limited number of payloads, or the payload carrying capacity of any vehicle is finite, we aim at optimizing the total payload required for localization. At any point, we drop the landmarks in pairs perpendicular to the body of the vehicle. Once the payload is deployed, the UV jointly estimates the vehicle and the landmark states. Therefore, the estimation architecture resembles SLAM. So it at least adheres to the same observability criteria as SLAM does. Therefore, what naturally follows is that we investigated SLAM problem, especially visual SLAM and range-based SLAM. We looked into their advantages, limitation, consistency, and observability conditions. We are expecting similar behavior from our system. As a remark, for open-ended trajectories like SLAM, our system too will be unobservable, that is without feature revisits. But our primary goal is to keep the position uncertainty of the vehicle within a desired bound in spite of the system being unobservable. The work done by M. Burke and N. Bose is the first and perhaps the only work that maps the position uncertainty to a physical and geometrical problem. Their objective was to optimally distribute a fixed set of landmarks in a known environment with containing obstacles such that they can minimize the average position uncertainty over the entire region. So this is more like a landmark distribution problem where the number of landmarks to be distributed is already known. The primary purpose of our work is to build a map on the go by injecting meaningful features in an otherwise feature deficient environment that will also facilitate future missions. It will enable UVs to accurately localize themselves using these deployed features. So we observe that even though the position uncertainty increases with time, the rate at which it increases can be controlled by the frequency with which the landmarks are deployed. We consider range beacons as landmark for our problem. So to analyze, we conducted a set of 3 experiments in a straight tunnel-like configuration as shown in figure 37B. So we considered a maximum sensing range to be 90 meters for all the cases. For the first case, the vehicle dropped landmarks uniformly at 45-meter interval. For the second case, landmarks were dropped uniformly at 72-meter intervals. And for the third case, they were dropped at 99-meter interval. Note that for the third case, the uniform drop distance is greater than the maximum sensing range. We observed that when the vehicle received path to at least 2 landmarks, known or unknown, the associated position uncertainty was quite low, as shown in figure 37A. For the third case, as shown by the red line, there are segments in the trajectory where the vehicle is navigating blind. That is, it is not receiving measurements from any landmark. Therefore, the corresponding positional uncertainty value happens to be significantly higher. So these are some of the important observations, as this plot reassures the importance of having measurements. Our goal is to keep the final estimated PE, or positional uncertainty metric, value close to the user-defined Pmax value, which is the uncertainty associated with the position error. This problem is solved in parts based on information we have on the system. For the first case, we consider a straight tunnel as shown in the image. We have an idea on how far the vehicle needs to travel. Using this case, we model the output PE as a function of various inputs such as vehicle's forward velocity, maximum sensing range of the sensors, noise in process and measurement, tunnel length, the landmark drop frequency or overlap percentage, etc. The construct for the overlap percentage is shown in figure 37C. This is a highly nonlinear and interdependent relationship, and there exists no known technique to map these inputs to the position covariance of the vehicle. So we use data-driven approach to develop a mapping function. We use the straight line case to develop the mapping function, as it won't cause any measurement loss due to line of sight issues. Moreover, the sensing range at any given point will reflect the true sensing range at that point instead of something that is potentially less than that due to bends or turns. Now, not all tunnels will be straight. They can have bends or turns based on whether we know the exact topology of the tunnel, that is the length of each segments along with the turn angles and their positions, or partial topology, that is the expected travel length and the number of turns without the actual turn angles of their positions, we propose two extensions. In this slide, as figure 38 shows, this is the system architecture. We generate more than 100,000 cases by performing Monte Carlo runs for the straight tunnel, varying the different input parameters. We developed a mapping. We developed a mapping model using the two methods. The two different methods will be discussed in the ensuing slides, but we chose to proceed with the model developed using a deep neural network. Once the mapping function is obtained, we solved an inverse problem to get an appropriate overlap percentage or drop frequency based on the desired PE value and the predefined inputs using mixed integer linear programming. Finally, based on information availability, we adjusted the position of the drop locations of the landmarks to address the measurement loss due to line of sight issue. The UV is modeled as a 2D fixed altitude model. We also have developed a 3D model using 12-state quadcopter dynamics for landmark dropping and for the SLAM problems. And this will be discussed in the future work section. But we assumed constant height or at least ground robots to begin with to simplify the optimization problem. The landmarks are estimated once they're deployed. Since they do not move, the rate of change of their position of the landmarks is assumed to be 0. We perform range-only measurement. S and W represents the process and measurement noise, respectively. Before diving into the details of the solution, let me first explain what is the parameter that we are trying to optimize, the metric. So every filter estimates the state of a system along with the corresponding uncertainty or the covariance matrix. Since we are trying to ensure meaningful position uncertainty bounds for the vehicle, we only concern ourselves with the submetric sigma p, corresponding to the vehicle's position estimates. So we have PT defined as the trace of square root of sigma p, because we found out that the cross correlation terms are negligible. Had they not been negligible, we can use the determinant of the submatrix sigma p. Now, PT increases with time for an unobservable system. However, it immediately decreases after a pair of landmarks are dropped. So we consider the maximum uncertainty at any given time t to be the maximum value for PT till that time. This is represented by the yellow line in figure 39. However, to get a continuous upper bound, we obtained a curve by joining the red dotted lines in figure 39. We see that after joining these red dotted points, the inputs have an exponential relationship with PT. For example, if I refer to figure 40A, keeping every other input parameter constant, and just by varying the overlap percentage, we see a change in maximum PT value with respect to the travel distance or the time. Similarly, in figure 40B, we get the same result by varying the sensor update rate. And similar results for varying the other input parameters by keeping the different, say for example, if we have 6 parameters, keeping varying 1 and keeping the other 5 constant. So we see that each of these individual curves are exponential in nature, and therefore we can divide this region approximately into 2 segments. One is the transient phase and one is the steady state region. Although we can say that the steady state phase is not actually steady, it grows at a slower rate. So the basic model for the maximum PT with respect to the distance can be written as an exponential function as shown in equation 1. Here, alpha 1, alpha 2, and beta 2 are constant real numbers. Now, inspecting how each of the input parameters affect the characteristics, that is, whether they affect the transient phase only, the steady state phase, or both, an approximate curve fitting model is developed as shown in equation 2. Using this model and selecting random input parameters, we see that the model output follows the actual outputs pretty accurately. The blue lines represent the actual maximum uncertainty bounds, and the red dotted line represents the maximum uncertainty bounds as evaluated by our model function. However, using deep neural network, we obtained a better performance, as can be seen by the error histogram plot, as well as the output, the actual versus model output comparison. Ideally, the actual versus model output should follow the red dotted line. We see that the function approximator developed using DNN, or deep neural network, is doing a better job. So we proceeded with the neural network as our function approximator. We have 6 inputs. They are velocity, maximum sensing range, noise in velocity, that is the forward velocity of the vehicle, noise in the sensing range, maximum distance of travel, and overlap percentage for straight lines. We have 2 hidden layers, each with 20 nodes and 1 output layer. We selected this network after going through a rigorous hyperparameter analysis. Using 2 hidden layers with 20 nodes, we designed a network that has a decent trade-off between computational cost and performance. We use ReLU as our activation function, not only because it's better and faster, but it divides the network into piecewise linear functions. This greatly helps to reformulate the model as a mixed integer linear programming model to solve for the drop frequency given other inputs and desired maximum position uncertainty. ReLU can be expressed as a set of linear equations and constraints as shown in this slide. Now, using the MILP, we find the value of the overlap percentage, or lambda, that minimizes the cost P max minus PE square. For a given vehicle and a set of sensors, usually the parameters such as forward velocity, maximum sensing range, and the noises are predetermined. Hence, they are kept constant. We change the lambda to minimize the MILP cost. The optimal drop distance gives us the number of landmarks required to be carried for the straight case, or N straight. The reason we are formulating this problem as an MILP instead of a neural network is that MILP can guarantee a globally optimal solution for a given mapping function. It does not need to do any kind of brute force or discretization of the space. Neural network with brute force will not be able to deliver such guarantees. We can use standard optimization methods with MILP. So for straight tunnels, this uniform drop distance is sufficient to keep the PE close to P max. However, tunnels with bends or turns can lead to line of sight measurement loss due to line of sight issues. Therefore, we need to address this. If we have partial information, that is, we know the length and the number of turns, but not the exact angles or the locations, we can come up with a conservative upper bound approach. For each turn, we drop a pair of landmarks right after the turn. So the total number of landmarks that are required to be carried by the UV will be N straight plus 2 times the number of turns, because we are dropping a pair of landmarks at each turn. This keeps the PE value lower than the Pmax, the desired Pmax value, due to the conservativeness of this approach. If we do not have access to, say, the blueprint of the tunnel, if you do have access to, say, the blueprint of the tunnel, we can do much better. So note that having access to the blueprint of the tunnel does not necessarily mean that the tunnel has adequate and meaningful features to support unmanned vehicle localization and hence navigation. So if we know the turn angles and their locations, we can adjust the location of these landmarks to ensure that measurement is never lost due to LOS. Every turn has a segment leading up to the turn and another segment following the turn. During the optimization phase, if we can assume that we have already placed a pair of landmarks before a given turn. So what we can see using figure 51A is that using the geometry, we check whether the vehicle will lose line of sight before reaching the next landmark dropping point, as shown by the green location in figure 51A. So as shown in this figure, we will lose line of sight from the right landmark shown in red for a right turn prior to losing the LOS from the left landmark before reaching these green locations. So for a left turn, it will be the opposite. So we pull the drop location back to a point where we will lose the line of sight immediately after the turn, as shown in figure 51B. We repeat these steps for the entire trajectory. This is what the drop location adjustment algorithm is doing. The next 3 set of videos will demonstrate the importance of landmark adjustment. This video shows the uniform landmark placement locations as generated by the straight tunnel case without landmark adjustment. Notice that we require 10 landmarks, but without taking care of the LOS, the PT value explodes. So in the next case, we see the conservative landmark dropping. Notice that we need 6 more landmarks in this case. That is, we need 16 landmarks for the same 400-meter run. So the payload capacity increases quite a bit. However, the uncertainty is kept within check. In the third video, we see that using the drop location adjustment algorithm, we not only keep the PT in check, but also notice that we did not require any extra landmarks than what was required for the straight case. However, for different scenarios, we have noticed that we may end up needing 2 to 4 extra landmarks in the end, if at all we need extra landmarks. So figure 52 illustrates the difference for Pmax quite vividly. The desired value for position uncertainty is 0.35 meter. It can be seen that using the optimal or conservative approaches, the vehicle is able to navigate, keeping the uncertainty in check. Now, we also notice that there are some edge cases where the optimal algorithm does not provide the desired result. This is due to the fact that 2 landmarks can effectively become collinear at some point as the vehicle travels to the next section of the trajectory after the landmarks are dropped. R. Sharma and all prove that even with 2 known landmarks, if this happens, the 2 landmarks effectively behaves as 1. So this can be addressed in many ways. For example, we can check for the collinearity and simply drop extra landmarks right after the turns. However, this solution can bump up the payload requirement and also computational cost for the extra landmarks the vehicle is adding. The next, we can design a rotating arm mechanism to drop landmarks at different angles based on information availability. The solution we incorporated to address this issue is by taking pseudo-wall measurements, typically at a lower frequency. This sort of mimics the action of a bearing sensor at significantly less computational overload in comparison to the 2 other methods. Not only that, it can also facilitate navigation without the need of additional position bias modeling or correction. This way, we can hit 2 birds with 1 stone. So, for the wall update, we take measurements from we assume that the vehicle has, for example, ultrasonic sensor pointed to the left and the right, that is perpendicular direction to the direction of the travel. So it takes measurement from the left wall and the right wall. Then computing the difference, we determine whether the vehicle is perpendicularly positioned where it is supposed to be. This in turn, combined with the landmark dropping algorithm, corrects the heading indirectly. The extra measurements also keep the covariance within bounds. This is a run with optimal landmark placement using landmark adjustment algorithms, but without a wall update. It can be seen in the last segment, that is the segment we're about to reach right now, that such an edge case arises. This can happen especially for turns with 90-degree turn angles. So we developed an engineered solution for this case, as this edge case do not happen all the time. For this case, we are considering the Pmax desired value to be 0.5 meters. This is the same case, but with a 10 Hertz wall update this time. It can be seen that the covariance are much tighter. So even though the position covariance increases, especially as seen in the perpendicular direction, even in the last segment, it does not cross the desired limit set by the user. And figure 55 clarifies this issue. We can see that the collinearity happens in the last segment. And in this segment, the actual Pmax value exceeds the desired limit for the case without the wall update. That is the blue line. This issue is taken care with the help of the wall updates. In this comparison, we see that the same wall updates can be used to address estimation bias as well. We zoomed into the trajectory plot, that is, it is from 0 to 400 meters in the north and 0 to 40 meters in the east direction. We can see that the unchecked biases can lead to filter inconsistency, as shown in the X plot in figure 56A. But just by adding a 0.1 Hertz wall update, that is updating it at every 10 seconds, we are able to rectify this issue. Training the neural network with the wall update can help the UAVs to travel a longer or the same distance with even a smaller number of landmarks. However, we observe this edge case at a later stage of this work. So exploring and analyzing the effects of wall updates and the frequency of these updates can be done in the future. Also, we consider, by the way, we consider smooth walls, and practically there might be objects in the environment such as tables or chairs or trash cans, etc. So this also needs to be taken into consideration in the future. So in this video, we see that the optimal landmark dropping algorithm, with the optimal landmark dropping algorithm, the vehicle can drop landmarks at the optimal locations and at the same time use them to return to the depot. During the return phase, this does not require to drop any extra landmarks. So the vehicle drops the required landmarks during the landmark dropping phase and returns to the depot without dropping any extra landmarks in the return phase. Now, the interesting thing is, much like SLAM, during the return phase, due to the trajectory closure that is revisiting known points and landmarks, the system behaves like an observable system. We can see that the associated uncertainty bounds decreases in time during the return phase. This video shows the UAV dropping decawave range measurement tags. The architecture was improved later to include arms on the UAV. However, this hardware setup was developed by Isaac before COVID, and due to COVID-imposed restrictions, we could not verify this algorithm with the actual landmark dropping on hardware. So this is the point where you can see that it drops the landmark. And in this project, we used hybrid optimization technique, and we aimed towards addressing point 3 and 4 in a global setting. These were the related papers published pertaining to this work. Now, moving on to the hardware section, the workflow shows the standard navigation architecture used for hardware and simulation. Since obtaining measurements from range and bearing sensors and developing appropriate data association techniques are crucial step for localization in a GPS-denied environment, a lot of focus was channeled in developing the sensors and their corresponding data association steps. We have developed the camera model for vision-based localization using range and bearing sensors. And we have also developed appropriate message parsers, decoders, the publishers, and the subscriber with ROS compatibility for radio frequency and even the camera-based models. So the structure in this slide, we present the camera model. This was borrowed from Dr. Randall Beard's Small UAV book. For simplicity of explanation, let us consider we have a square image frame. That is the azimuth and the elevation angle or the focal length to be the same. So F equals to M divided by 2 tan V by 2, where V is the field of view and M is the width or height of the frame in unit pixels, since we are assuming a square frame. We can determine the centroid of the image frame. Using various techniques, we can also obtain the centroid of an object. And using these values, we can calculate the bearing angle as shown in equation 2. Now, if we have parameter P or a function that is mapping the unit meters to pixels or vice versa, we can use the object size and focal length augmented with these measurements. Even the distance to an object can also be measured. So the first and the most simplest data association that we did to validate the bearing measurement is shape and color detection. Spheres are projected as circles onto a 2D plane from all directions. So we use spherical objects with different colors. We obtain the centroid using hue transformation. Using the hue, saturation, and value color space, we associated the colors with the shapes. However, since we can easily figure out that we'll run out of distinguishable color groups pretty quickly, and because it is sensitive to light, the distinguishable backgrounds and reflective surfaces, we resorted to different and better data association techniques. Moving on to the QR code and barcode detection, we can immediately see that we did not need an RGB color space. Rather, we can work on a grayscale image or video. This improves the data association, or in fact makes it faster. Although QR codes can store significantly more information than barcodes, as it stores data in a 2D surface, they aren't robust to distortion in detection caused by wider viewing angles. Since barcodes store data in a single direction, we leverage this property to print barcodes vertically and then wrap it around a cylinder. This way, we're able to detect barcodes from all directions, although we won't be able to detect barcodes the same way from the top. At least we are assuming from all directions with a forward-facing camera. We use this method to obtain bearing measurements, and we used OpenCV and ZBar libraries with Python to generate and detect barcodes and QR codes. This vehicle localization experiment was conducted in the white room, which do not have the motion capture system, as you all know. As we can see, the vehicle starts from a location, uses the barcodes to localize itself, and route through the set of waypoints and following the sequence of waypoints. This is the vehicle camera view. As we can see that in this setup, we did not guarantee the path to 2 landmarks. This experiment was done before the VPLC problem to validate our setup. This was later used to conduct experiments in the mocap room and we used mocap to generate the ground truth for comparison of the effectiveness of our estimation algorithms. Moving on to AirTag detection, AirTags are uniquely designed to provide range, bearing, and orientation information. They're robust to distortion, and the ROS libraries for AirTags provide tools enabling efficient data association. We can create up to 1.4 billion tags using air markers. We designed each landmark to have 4 associated tags with 1 master and 3 slave faces. For aerial experiments, we can also add a 5th face as the top. If it is necessary to provide the size of these tags to the data association file prior to the navigation of the online step. So the tags shown in this picture are 12 x 12 centimeter square tags. The crux of this setup is that using our relative distance and orientation of the slave faces, we map them to the master face. That is, whenever a measurement is obtained from a landmark, it is always with respect to the master face, regardless of whichever face has been observed. So this step further improves the data association as we are not requiring to do it every time during the runtime or the online step. Figure 63 shows simultaneous detection of 10 such tags using one Astra Orbit camera for ranges approximately 0.5 to 4 meters with the desired output in the range of 1 to 3 meters. And we can, even though Astra cameras are RGBD cameras, we did not use the depth feature of those cameras. Next, we developed the ROS compatible parsers, publishers, subscribers for radio frequency based range sensors. They have simpler data association techniques, no field of view restrictions in general, and most importantly, not influenced by light. The 2 sensors that we have worked on are Decawave for short range measurements and ENSCO radios for long range measurements. However, we saw that especially for indoor experiments, camera-based setup provided measurements with less noise than comparing it with the Decawave. We developed the hardware base using the Turtlebot, Polulus, air drones, and DJI Matrix. I have mostly used Turtlebots to test and validate my algorithms, primarily because of its payload carrying capacity. We developed the hardware platform for a single and multiple vehicle operations using ROS, Python, Ubuntu, and OpenCV. The system has the capability to be controlled by individual computers that are mounted on top of the vehicles, or we can do so using ground stations using master-slave communication. The motion capture system, or mocap, provided the ground truth for comparison. Now moving on to the conclusion and the future work. To highlight the major contributions, we have developed algorithms to support GPS-denied navigation in various constrained environments. The VPLC problem addresses routing and landmark placement optimization with the help of the combinatorial optimization technique developed in a MILP framework. In cooperative timing arrival problem, we explored a relative cooperative navigation strategy and PN guidance algorithm to facilitate simultaneous arrival of multiple agents in a target-centric frame onto a moving and maneuvering target in a GPS-NAT environment without the need of any global landmarks. For search area optimization, we explored evolutionary algorithms and gradient-free optimization strategies to provide solution to an area coverage problem. For our final problem, we have developed a hybrid optimization strategy borrowing benefits of machine learning and MILP techniques to facilitate navigation in constrained and challenging environment based on information availability. Even though we did not concern ourselves with the desired heading uncertainty bound, as heading was anyways updated indirectly, we noticed that for all the experimental cases, the heading had a very tight uncertainty bound. For most of the cases, it was plus minus 10 degrees for the 3 sigma bounds. Finally, we discussed the contribution made towards the, developing the hardware architecture for experimental validation during the course of this research. Now, moving on to the future work, we can validate the effectiveness of our feature deployment algorithm using a 3D model. As video 17A shows that the range-based SLAM was achieved using a quadcopter. We have also developed the similar 3D model for a feature deployment using quadcopter, but we might need to provide additional constraints for the optimization problem. Also, if the payload is limited per UV, even though we are minimizing the payload carrying capacity, the number of payloads it can carry is still limited. So if the payload carrying capacity is again restricted, we can think of efficiently carrying payload over multiple UAVs to extend the range of our work. To build approximate maps like the downtown public map or the highway maps or basically the subway or the bus tour maps, we can utilize node-to-node localization and travel using keyframing technique. As shown in figure video 17B, we can perform active short interval path planning to navigate without any prior information. Once the vehicle returns to the depot, we can do further post-processing operations if required to form smoother and more accurate maps. This map, augmented with the injected features, can act as known landmarks in a known environment. Therefore, UVs in future missions can then utilize this information to simply localize themselves instead of needing to estimate the position of the landmarks as well. For the hybrid optimization problem, we assume that the landmarks are deployed in pairs. However, we noticed that if we drop them in a staggered configuration, we can further reduce the maximum position uncertainty. But staggered configuration, for this case, we considered, as shown in figure 68 on the left, we considered a half range drop for the staggered configuration. However, there might be infinite such solution and we don't know what is the best solution in this case. So in this case, we see that this highlights the nonlinear complexity of our problem at hand, as there can be so many factors that we can consider to improve upon our work. The staggered formulation adds more dimension to the already NP-hard optimization problem, as I've just discussed. So on the figure on the right shows dropping arm mechanism to adjust the angles of the drop. But then again, this was empirically developed after getting the optimal landmark placement locations. So for optimal strategies, this can also change by what factor the landmark adjustment need to be done for each and every angles for the drop location. So these severely complicates the problem even further. So we provided a solution, a sufficient solution that works. However, they can be improved by incorporating these techniques. A couple of lab mates are already working on simultaneous arrival problem to extend this problem to 3D to perform active collision avoidance while ensuring the time to go consensus remains valid. They are also developing a consensus that would allow desired angle of collision. We have observed that if the graph remains connected, as shown in figure 69A, the solution also works for a subset of the agents trying to converge onto the multiple targets. However, we did not develop a theoretical proof for that. This can also be done in the future. As shown in figure 69B for the search area optimization problem, we can use the heat map to find potentially cooler regions and actively feed it to develop uniformly distributed map. So this way we can improve those individual topics as well. These are the related papers that were published over the course of my PhD. And these are some of the references that I have used pertaining to my presentation today. So thank you for listening to this hour-long presentation.
Thank you, Sohum. That was a good job.
Thanks, Dr.
So I would say next, all the general audience other than committee members can ask questions, and then we will dismiss all the general audience, and then the committee members can ask the questions. So anybody who is not in the committee is open to ask questions now. Give Sohum some hard time now, guys.
Dr. Sharma, are we still recording?
Yeah, I will stop the recording now.
Okay.